not only can we convert individual points from Cartesian to polar or polar to Cartesian, we can convert whole equations. So a relationship between, say, x and y, that would be a Cartesian equation, can be converted to a polar equation, a relationship between r and theta. Now, the things that you need in order to do this are that x equals r cosine theta, right, and y equals r sine theta, and that r squared is x squared plus y squared, and that the tangent of theta is y over x. So if we look at this equation, this is the equation of a hyperbola. I wonder how it would look in polar. Well, everywhere we see an x, we could use x equals r cosine theta, and we could use y equals r sine theta. So x squared would be r squared cosine squared theta, and y squared would be r squared sine squared theta equals 1. Now I could factor out the r squared, and I'd have cosine squared theta minus sine squared theta. And this is actually an identity. So cosine squared minus sine squared, if you remember, the cosine of 2 theta is cosine squared theta minus sine squared theta. This is a consequence of the angle sum identity. So if you have cosine alpha plus beta, you get cosine alpha cosine beta minus sine alpha sine beta. In the case of 2 theta, remember 2 theta is just theta plus theta, so the two angles are the same, hence the cosine squared and the sine squared. So we have r squared times cosine 2 theta equals 1. Okay, and that tells us that r squared equals 1 over cosine 2 theta. When we have a polar equation, we like to have it in the form where we have r as a function of theta. So if we wanted to, this r isn't quite a function of theta in this case, it's actually two functions of theta. We could solve here. This would be plus or minus 1 over the cosine of 2 theta. So this equation, this Cartesian equation for a hyperbola, this is the polar equation for the same thing. I guess we could also, since one of the cosine is the secant, we could say that r is plus or minus the secant of 2 theta. Pretty common in polar to try to get r so that it's a function of theta. We'll see why when we go to graph these representations. This is a nice way to have it. Here's another one. We want to convert this to polar. It might be best in this case to multiply it out first, because I'm thinking whenever I have an x squared plus y squared, that's automatically an r squared, so it might be best to multiply this out. We'll have x squared minus 10x plus 25 plus y squared equals 25. So first thing we notice is that we have x squared plus y squared, right? So x squared plus y squared is r squared, and then minus 10x, x is r cosine theta, and then we could move this 25 over to there, right, and we would have 0. So we have r squared equals 10r cosine theta. So let's see. What we'd like to do is to be able to solve for r. Maybe I shouldn't have done that quite so soon. If you were solving this for r, since it's quadratic, you'd probably try to factor it, which you can do because r is a factor of both the first term and the second term. If you pull out an r, you have r minus 10 cos theta here. So either r equals 0 or r equals 10 cos theta. Now, r equals 0, that would just be the origin, right? Because no matter what direction you face, if you don't walk out, you're still stuck. If you take 0 steps out, then you're still stuck at the origin. So this is just the point at the origin. However, this equation has that point included, because if we use an angle of theta where the cosine is 0, for example like pi halves, then we're going to have r equals 0, we're going to be at the origin as well. So this one is a little bit redundant in that this equation already captures that. So the equation of this shifted circle becomes this polar equation, r equals 10 cosine theta. You can also go backwards. If you have a polar equation, you could convert it to Cartesian. Here's an example. We've got r squared equals 4r sine theta, and we want to convert that to Cartesian. Remember, r squared equals x squared plus y squared, and r sine theta, that's the same thing as y. So this equation becomes x squared plus y squared equals 4y. Now I know that's a circle. In order to see it, I know it has to be some kind of an ellipse, right? Because you have x squared and y squared together on the same side with the same sign. So we know it's an ellipse, and since the amounts are balanced, right, it's got to be a circular ellipse. Let's see, if we move this over, we could complete the square on y. If we have y squared and a constant times y, we can take half the constant and square it. So half of negative 4 is negative 2, negative 2 times negative 2 is 4, so I'll add 4 to both sides. And we end up with this circle, x squared plus y minus 2 squared equals 4. This must be the polar equation for a circle of radius 2 centered at the point 0, 2. That's kind of handy. We actually recognize it easier in its Cartesian form than in its particular polar form. Okay, and let's see, here's another one. X equals, or r equals 4 tangent theta secant theta. Now I know that if I could find an r cosine theta in this problem, then I would have x, right? And if I can find an r sine theta in here somewhere, then that can be converted to y. So I'm on the lookout for that. And we have r, let's see, it's important to have sines and cosines, so let me write this as r sine theta over cosine theta, and then this secant theta, let's see, this secant theta is 1 over cosine theta. If I multiply both sides by this cosine theta, I get r cosine theta equals 4 sine theta over cosine theta. But r cosine theta is x. Alright, I'm on my way a little bit here. Another thing I can do, look, I've got a sine theta and a cosine theta. If I multiply this fraction top and bottom by r sine theta is y, r cosine theta is x. So we're making progress here. Now we have, if I multiply both sides by x, I have x squared equals 4y. Oh, this is the equation of parabola. So this polar equation here is the polar representation of a simple parabola. One more. Got a polar equation, and we want to convert it to Cartesian. I see the r and I see the sine, but it's not sine theta, it's sine 2 pi thirds minus theta. I wonder if what might work here would be an angle sum. If you have the sine of alpha minus beta, you get sine cosine minus cosine sine. And in our particular case, then the sine of 2 pi thirds minus theta becomes the sine of 2 pi thirds times the cosine of theta minus the cosine of 2 pi thirds times the sine of theta. So using this angle difference identity, we have, let's see, what is the sine of 2 pi thirds? That is root 3 over 2. And the cosine of 2 pi thirds is negative 1/2. So we really have, in this equation, we have r times root 3 over 2 times the cosine of theta. Minus minus would be plus 1/2 r times the sine of theta equals 5. So what we've done here is I've expanded this, right? And I distribute, this was now became a sum of cosine and sine, and I distributed the r to both terms, and then we have 5. Now it's easy because r times cosine theta is x, so we have root 3 over 2 times x plus 1/2 y equals 5. Oh, that's the equation of a line. So we converted to this Cartesian equation of a line by using an identity.